Welcome to this, our last talk in the Vision Revolution series for Clonmel Junction Festival 2020. We're here today to talk to you about radio waves, which are the final installation in our series of talks about the whole electromagnetic spectrum, of which most of the light is invisible. And often we wouldn't even think of radio waves as visible or invisible light, really. Yeah, we just think of it as sound, but it's not sound.
We think of radio as sound, but actually radio waves are invisible light, just like gamma rays or infrared or any of these other types of light that we've talked about this week. The radio waves are used for communications, for radar, for navigation, for Wi-Fi.
And they're used in astronomy as well, but we've done a lot of astronomy, so we're not going to look at astronomy
today. They're electromagnetic radiation with very long wavelength, the longest wavelength. Really that long always. I mean, it can go from 1 millimeter.
But 1 millimeter is a microwave.
That's a microwave, but it's still considered a radio wave. 1 millimeter right up to 10,000 kilometers.
And apparently it can even go beyond that. It can go up to 100,000 kilometers.
Ultra long waves. Yes, indeed.
But we don't produce those because the antenna would be impossibly long to possibly
right.
Yeah.
So radio waves are measured in Hertz, and I always had a problem actually figuring out what Hertz were for a long time, until I looked at this diagram and I realized it's to do with frequency. So it's a measure of frequency, how many times the thing is going up and down. That's what Hertz designates. So at 300 gigahertz wavelength, that's like 300,000 hertz, means it's going up 300,000 times a second, really, really fast, like that. So obviously it's got to be really small, as opposed to a 30 hertz wavelength is only doing like 30 oscillations a second, so it's going quite slowly, not as slowly as me, but...
So it's the opposite of, when you say 1 millimeter, you're talking about 300 gigahertz. And when you're talking
really
about,
fast.
You're talking about 10,000 kilometers, you're talking about 30 hertz.
Yeah, so really long and slow.
And if you were talking about 100,000 kilometers, you'd be talking about 3 hertz, wouldn't you?
That's it, exactly, but it's just far too long.
A radio wave, we're often used to, the image we were just looking at was a sine wave. It's not really... It's just a kind of a diagram that helps us to understand frequency and amplitude.
Because waves actually are in 3 dimensions, but generally we have to represent them in some type of graphic way we can understand. So 2 dimensions really. And
this would probably give you a more accurate representation of what happens with a radio broadcast.
So they're spreading out in a lot of different directions.
They're in a very complicated way, but this is still, of course, a 2-dimensional representation of something that's happening in 3 dimensions. So you get the idea of the complexity of the forms of these. And if we look at the history, we talked before. In the second talk, when we introduced the electromagnetic spectrum, we said that the reason we call it the electromagnetic spectrum is that it all flows out of the work of Maxwell, the Scottish professor of physics. James Clerk Maxwell, who was a Scottish professor of physics at Cambridge in the late 19th century.
That's right. And he made the connection between electricity, magnetism and light, and showed that they were all part of the same phenomenon.
Which is the electromagnetic spectrum. And now another scientist, a German scientist who was very interested in Maxwell's theories, and he wasn't the only one, was Hertz.
Yeah, Rudolph Hurts. He was a lecturer in physics at Karlsruhe University, and one day he was demonstrating to some students induction using a thing called Rice's spirals. Now what these are they're like coils of wire, essentially. 2 coils of wire, and you put them together close to each other. So the Rice's coils induce a current, and sparks go between the plugs, essentially, the ends of them. And so he thought, what if I did this in a much bigger way? And so we set up this amazing experiment with these giant zinc balls, which he was using as capacitors. So they were going to have a capacity to hold electricity in them. And then he's got a wire, if you can see it here, and these two little other balls at a distance. And
which are smaller.
They're smaller.
And they're very close together.
Yeah, well, they're a couple of millimeters apart, right? So there's an a copper wire, and an electric current is set up in the copper wire. He applies a current across it, if I understand correctly, and sparks jump across between those two other little balls in the middle there. So it shows that there's an electric current there. Now, what happened is he set up this another coil. We can see it in the foreground here, with a spark gap, and suddenly sparks started to flow across that as well, or jump across it. So he proved that
this would have been Maxwell's theories of electromagnetism in action. But of course, it was also wireless.
It was wireless communication. What he showed is that there was an electromagnetic field set up, and that was setting up another current in another coil, but it was communicating. So therefore, we had wireless energy passing from one coil to the other.
Yeah.
So that was really what he did. But he wasn't really that concerned with communications at all. And in fact, he said in 1887, I do not think that the wireless waves I've discovered will have any practical application.
My God, that was in 1887.
Yeah.
Like radio communication was invented, 7 years later?
Absolutely, and Marconi,
we're going to come to that now.
It and,
but look, already before we even go on to Marconi, look at the beauty of this experiment. And this is something that we're going to look at now in this talk quite a lot. Is what beautiful forms, these beautiful platonic forms.
Absolutely beautiful things. These spheres.
And it's quite extraordinarily associated with its time, but they're also timeless in a way. And now we go on to talk about a person who came from a very different culture because he wasn't an academic at all. Marconi.
Exactly.
Guglielmo.
I looked it up this morning. Guglielmo
Marconi. Very good. You've done your research.
He's an Italian aristocrat. His dad, Giuseppe Marconi, married an Irish woman.
Oh yes, one of the Jemisons, wasn't he?
Annie Jemison, that's right. And Guglielmo was brought up. He was quite protected as a youth. He didn't actually go to school or university. He had private tutors at home.
Okay.
Either in
quite a beautiful home too.
They lived in a magnificent, almost palatial residency close to Venice.
Wow.
So either there or else some other residencies, I think in the London area. He was incredibly interested in electronics and in radio, in all of this, electromagnetic spectrum. And so his mom, who was a very dynamic woman, organised that he would have tutoring in this area, but then he would also become the assistant to a professor in physics at Bologna University. So he learned a lot that way, and he started trying out stuff at home, basically building, with the help of his butler, building these electromagnetic devices at home.
So once again, a beautiful thing, and especially from the eye of a contemporary artist. In the early 21st century, you look at this and you think, wow.
So this is more or less an installation for sending a telegraph, so
which would have been wired communication.
Yeah, exactly.
But he modified it to add this plate, this aluminium plate, is it?
That's right. That's an antenna. So what you have is a spark one of the spark plugs here generating electricity on the left.
So that would be similar to what we saw in Hertz's experiment.
That's right. So that's generating electricity, and then that's passing electricity to an induction coil, and then it's powered by a battery actually. So it's generating a signal, and then onto this more or less wireless Morse code. A little device here on the right. And I think the important thing about this is a standard Morse code setup. But the important thing is that he added this monopole antenna. So it's like this big square piece of metal here. That's an antenna, and that allowed him to send a signal 3.5 miles
like 5 kilometres. That's
Yeah.
like halfway across town.
Yeah, which was pretty good for the time.
Yeah,
I mean, at the same time, this is 1894, and everything goes very fast from there.
Yeah. So he first of all he tried to contact the Italian Minister of Post and Telegraphs, and they just threw his letter in the bin, didn't they?
Well, I don't know if they threw it in, but they didn't read it, and they wrote, or well, at least they didn't act on it, and wrote Alla Lungara, which is Via della Lungara,
Which is the lunatic asylum.
Yeah.
Yeah.
So that was
So
a pity.
he left Italy, went to London.
with his mum. I mean, so Annie Jemison was very, determined to support her son. So she brought him to London, and she arranged a meeting with the chief electrical engineer of the British Post Office. And from there, the rest is history,
Britain
really.
was a maritime empire, a global maritime empire. So their interest was communication with their empire, and especially communication with their ships, ship to shore, because I mean they could communicate across land. They even had cables going under the sea across the Atlantic, across the Channel, right across Asia, but they couldn't communicate with ships, and that's a bit of a disadvantage for a maritime empire.
Absolutely. So the British, they saw the value of this immediately, and they suggested he should patent it. And very good on them, actually. They didn't steal it. And so on the 2nd of June 1896, he patented with the title "Improvements in Transmitting Electrical Impulses and Signals, and in Apparatus Therefore."
Okay, and here we're looking at, this is already a year later in 1897.
Okay, and this is the Post Office engineers.
Engineers of the British Post Office are working with equipment from the Marconi company.
Amazing.
Once again,
beautiful apparatus.
Beautiful apparatus.
The first successful transmission across the English Channel was from Wimereux in France to South Foreland Lighthouse in England, and that was in 1899.
1899.
Yeah, and it was from, the St. Paul, which was an American passenger liner. It sent a Morse code message to an English radio receiver 66 miles away from the British coast.
Okay, so about 90 kilometres. Yeah. So it moved very, very fast, and look how sophisticated the equipment is already. I suppose a lot of it would have been based on telegraph equipment that would have been not wireless but wired communication. But look at the heroic scale of what they were doing.
Yeah. Well, the big interest then was transatlantic communications. They'd figured out how to do it, within Europe and across the sea, close by, but how to get across the Atlantic. And so Marconi got funding to build a station in a place called Poldhu in Cornwall. And the idea was that they would have a really big station there, and with a really, really big transmitter, and try to send a signal right across the Atlantic. Okay. And I think they were relatively successful with that. They got to Newfoundland.
To Newfoundland was the first station of call. And look at the scale of this project. This is an antenna. So the drawing shows an antenna based on a cube.
That was probably the original design.
Like an inverted pyramid within a cube. And then I don't know whether these are just two variations of one variation that got built, but the photograph is of a cylinder. And
a little bit like a gas silo or something like that.
And you look at the scale of the buildings, you get some idea of the enormous monumentality of these projects. So it was all about transatlantic communication.
That's right. But the thing is, with Poldhu, is they got a grant from the Canadian government of $80,000 to build a station in Nova Scotia, and
which was a little bit further west than Newfoundland.
That's right. And they couldn't pick up a signal from Poldhu at all, so they had to move a bit further west. So they chose a site in the west of Ireland.
Clifton, yeah.
That's right, yeah. I mean, look at the size of this installation that they're building. So, these things, this is the condensing house. Is that this is the condenser house? And it's just...
From what we understood, they were creating enormous voltage and sending them along these mast fields to send very, very long waves across the Atlantic.
So when they built this in the Marconi station in Clifton, which is in the west of Ireland. They built this huge condenser house and then a powerhouse with 6 boilers.
Which worked off turf.
That's right, yeah. So it was very convenient, actually. Yeah. And then 8 masts, and the masts were 210 feet high each. So these were massive, and they were sending these like crackling signals. Apparently, you could hear the crackle for miles around.
So it were extraordinary feats of engineering, and it gives you some idea of the vigor that there was in industrial culture.
Absolutely. And the energy, just get it done. I mean, it was less than 10 years ago. He was a kid, and he was going along with his mom to see these people and try and sell them this idea. And here we are, 10 years later, and sending signals right across the Atlantic. Incredible.
Yeah, setting up bases in Newfoundland and in the west of Ireland.
But he didn't do. He didn't do the first audio broadcast, Marconi.
Good evening.
All of this was Morse code signals, wasn't it? So they were, they weren't transmitting music or.
So around about the turn of the century, it was just Morse code, which telegraph communication had always been in the 19th century, and then in 1906, Reginald Fessenden created the first audio transmission.
Okay. And this is. This image is really interesting because that's the rice spiral. See?
Oh yeah.
In the foreground there.
Okay. I wonder how that works.
They're the 2 coils you can see.
Yeah.
I don't know why he's using them, but
you see the same forms coming again and again, cylindrical forms, cubic
coils,
coils.
Yeah.
So Fessenden sent the first audio transmission on Christmas Eve.
Allegedly.
Some people dispute this, but one history claims that the first audio broadcast was on Christmas Eve, 1906, and this is what it sounded like.
Good evening. This is Professor Reginald A. Fessenden speaking to you from Brant Rock, Massachusetts, at the tower of the National Electric Signaling.
Okay. So I think that's just a recreation of the because I don't think it was that sort of quality at all.
But what was important about Fessenden, whether that was actually that is the actual original recording or not, is that he figured out a way where you could send a voice. So he figured out that you could send a signal on a high frequency signal that sound would be encoded into. And then when it got to the other side, he figured out a way of picking that sound up or decoding it, isolating it back out of the thing. Like it sort of piggybacks on the wave. Actually, the sound does.
Okay.
So
extraordinary. So by the 1920s, audio broadcasts had been commercialized, and by the end of the 1920s, every household in America, at least, and a lot of European households had their own radio.
And then there was the whole culture around tube radios and the romanticism of them. Such beautiful objects.
And with a piece of furniture in the house like any other.
And of course they popularized music. I mean, music became suddenly accessible into everybody's home, which is extraordinary.
And then 30 years later, they already had the transistor radio, which is kind of the first micro technology, wasn't it?
So you could just carry it.
So things advanced very, very quickly, and while this sort of democratization was taking place, there was also an enormous engineering project that was putting radio equipment on military ships like this one.
This is the arc radio.
Look at the scale.
It's an arc radio for the U.S. Navy. So this must be a massive generator in order to create this electrical arc, but of high voltage.
It's an arc radio, yeah. So this is the kind of technology, and of course we're still looking at radio technology. This would be radio astronomy. That is monumental in scale. Nothing more monumental than what's just been built in China, the radio telescope.
Wow.
Guizhou. So I mean, look at it. It's the size of a mountain, isn't it? But what interests us more, and I forget, we're artists, and we've explained in some of the other talks that our interest in the electromagnetic spectrum is a show that we're doing called Invisible Light, where we're going to make 7 installations based on the electromagnetic spectrum and based on mostly on the invisible parts of the electromagnetic spectrum. And one of the interests that we have in radio is the kind of democratic DIY culture.
So we're going from the giant scale of this radio receiver to the domestic scale of a transistor, or even a crystal radio.
Even a crystal radio. So that is a particular culture we got interested in, isn't it? Really?
So yeah, crystal radios are the original do-it-yourself radio. They're
from
really,
the 1920s, wasn't it?
Yeah, even earlier. I think that this is the principle in which Marconi would have been basing his original receivers on. And so basically, it's the simplest thing in the world. It involves an antenna, which is a long wire, which captures waves, and an electric current builds up in that antenna from the waves it captures from the atmosphere. Then a coil, which you can use to tune, a detector that will then take that wave or that current and then convert that into DC current that becomes a sound signal, and some headphones. Really simple. And the thing is, you can make one of these out of sort of stuff you'd find at home, which is what I love about it. And in
fact, the American government in the 1920s published a brochure which would have been the origin of all this. This shows what's called a crystal radio. Now, why was it called crystal?
Well, it's called a crystal radio because the detector was the complicated bit at the time. They used a little crystal, which is a piece of shale, I think, and this shale would start to vibrate or resonate with the current, and then they had this little thing called a cat's whisker, which is a tiny wire, and that was like tipping off the shale, and so that would resonate, and that acted a little bit like it was like a valve, so that converted the AC current into DC current that you could then go into a headphone and you could hear. It became a sound signal.
So this is the kind of thing nowadays, if you do it with a germanium diode.
That's right. That was effectively a germanium diode, but they're really, really delicate. So you've got this tiny little wire like this, and so that was always going off and stuff. So those crystal radios kind of went out of fashion. They weren't that.
But we're very fortunate. And particularly for our project, which we're going to tell you about in a moment, that we live within about half a mile of one of the best shops for making your own radio, which is called Saint-Quentin Radio here in Paris, and they sell all these germanium diodes and probably cat's whiskers as well, and
capacitors. Capacitors. I always found that really difficult, that concept too, especially because they used to call them condensers.
Oh yeah.
But what it is, when you think about it, it is what holds. It's got a capacity. It's what holds. It's got the capacity to hold current. That's why it's called a capacitor. And so you need one of those as well. To get a slightly more powerful radio. So you can buy those as well. These are electronic parts that you buy in a radio shop or something like that, But you can make them yourself. That's the lovely thing.
Yeah, which is what we're hoping to do. And our project, this is a culture that's going on to this day, and you have people who are making crystal radios using credit cards and crystal radios using
I've seen them in pencil cases. I've seen them in matchboxes,
in pizza boxes.
I've seen an incredible one, which is a pizza box and a wire essentially, and a headphone. It's incredible. And so what he does in the pizza box is he uses the box itself as the antenna, so he wraps his wire around it, and he also uses it as the coil, and that just picks up the sound, and then he's got an earphone. It's like incredible.
And so what we want to get into this sort of connection of technology and everyday life.
And then the beauty of it, because these things are really beautiful as well. a coil. If a coil is a wound piece of wire, then it can be a lot of different shapes, you know, so that brings in all these incredible sculptural ideas. So this umbrella we see, the umbrella crystal radio, is fascinating because it's so clever. What he's doing there is he's using the actual shape of the umbrella as his antenna. So he's got a lot of wires going around there. You can see them wrapped around. Then he's using the metal stalk as the capacitor. So he's also got wire wrapped around there, and that's creating a current.
You can slide up and down.
And you can slide that up and down. He's probably isolating in some way.
Yeah.
And so that's creating a current that is resonating and resonating the signal from his antenna, and then he's got that attached to an earphone. So like the radio is the umbrella. I love it.
This one, but the man in skis, that would be much older.
That's an older one, yeah.
This is a man wearing what looks like a safari hat.
And so the guy in skis there, what he's doing is because I mean, one of the principles is that you need to have an earth. Now, if you don't have an earth, you've got to have what they call a dipole antenna, which is a much longer antenna.
Okay.
And so that's why they get into having antennas that are wrapped around stuff, you know.
Yeah.
And
this is a dipole.
Yeah, because if he's skiing, he obviously can't be earthed at the same time. Yeah. So he has his dipole
maybe
antenna.
with the ski balls. Maybe.
Yeah, maybe, but then they'd be breaking the signal every time he lifts it up.
Yeah.
And this hat as well, I love it.
Yeah.
He's got it built in.
Yeah.
I wonder where he's got
so
his...
So that's some sort of a safari hat, must have some.
So where's he got his earth, I wonder. But what's really interesting for us about this is this idea that that the radio can be an extension of your senses in the same way as, you know, we've got vision and we've got hearing and we've got touch. You know, picking up this other type of electromagnetic radiation.
That's all around you.
That's
And
something that you wear, an extension of your body.
With some of these images, you see how connected the whole technology can be made with your body. You know, it can become part of your everyday clothes. It can become a hat or an umbrella or something that you wear on your back. It can become a credit card. It can use kind of everyday DIY materials. And all of that, of course, reminds us of the very first image we saw, which was Marconi's first radio transmitter from 1894.
Absolutely, with this piece of metal, which looked like a piece of tin foil, essentially.
Yeah. And you know, also extraordinarily beautiful and simple.
Yeah. There's a nice thing I like as well, that it relates a little bit to Art Provora art, you know, where it's put together with bits and pieces, and there's wires here, and it's like an art that's made of poor stuff, but it's really beautiful.
Yeah. So this is our project, is really to build crystal radio, probably hats.
Possibly hats.
Try different
some
ways.
wearable extensions of your body that are radios.
Yeah. And this will be part of our Invisible Light show, which will be at the Crawford in October
2020,
November, and which will go on to Dubai next year as part of the Expo 2020, which is now in 2021.
That's right.
So that kind of wraps up our talk about radio, and we wanted to finish, because this is the last talk, we wanted to kind of briefly recap where we've been, because this is 7 talks. There's been an enormous voyage through.
Well, I think we've covered all the light in the universe.
Yeah. If you remember the very first talk, we talked about some of the famous experiments that were done, Young's slits and Fresnel's rings.
Which led to quantum physics, actually.
Einstein's relative universe and quantum physics, and the whole idea of the whole notion of the photon, a particle that has no mass when it's at rest, but of course it's never at rest.
And then Wheeler's participatory universe, which is an absolutely mind-blowing idea that the universe...
very controversial idea, really.
The universe just exists through our own observation of it, which actually all stems from the study of light.
All of these things come out of the study of light. We looked at a lot of the stories of the researchers who worked for 400 years on developing the theory of light and discovering different things along the way. We looked at the extraordinary effervescence of 19th century scientific culture, particularly. That gave us X-rays and gamma rays.
We looked at all those incredible medical advances that we've made, including PET scans and X-rays and all these different ways of looking inside the body using invisible light.
We've looked at some extraordinary creatures, haven't we, like the mantis shrimp, which seems to live for colour?
It sees ultraviolet. It probably sees infrared as well. It sees lots of colours that we don't see.
And it also produces a lot of colour, which presumably is connected. We've looked at some of the research that we've been involved in ourselves to do with vision.
Through some of the great scientists that we've worked with and had the incredible good fortune to work with.
And we've looked at some kind of everyday things that we see every day, like pouring milk into a cup of tea, how that looks in invisible light, how that looks, for example, in infrared. And we've looked at the oldest light in the universe.
That's right. Right back to the cosmic microwave background.
This is from the very beginning of the universe. And we've looked today at some heroic engineering projects associated with radio waves and radio communication.
So we've looked at the story of all the light in the universe, but what was missing?
What was missing for both of us was women. It was such an extraordinary voyage through 400 years of research and of discovery and of invention, but not a single woman.
We mentioned one woman once, Marie Curie.
Who was an extraordinary woman.
She wasn't part of that direct story, but she's got her own story. She's the only woman to have won 2 Nobel Prizes, one in 2 different disciplines, in fact, in physics and in chemistry. That's right.
An extraordinary career, but she was the exception.
And she faced an incredible struggle to become a scientist. So she was a brilliant student. She's from Warsaw, and at the time, it was the late 19th century, women were not allowed to go to university at all. Not only that, but there was a lot of restrictions in what you could study. People generally couldn't study science subjects, they couldn't study Polish language, and so people had set up a clandestine university.
The Flying University.
So she and her sister both had the opportunity to go to the Flying University, which is fantastic because the world would not have had Marie Curie without that.
And she and her sister formed a kind of a pact, didn't they?
That's right. They were very supportive of each other. Her sister's name is Bronislawa, and Bronislawa wanted to be a doctor, and Marie Curie wanted to be a scientist, and so Marie was a bit younger, and so they agreed that she would, while Bronislawa was in medical school, Marie would give tutoring lessons to support her, and then when Bronislawa became a doctor, she would then support Marie through her studies, and they did it that way, and both girls had incredible careers and were very supportive of each other and worked together right through.
And they both moved to France.
They both moved to France, that's right.
And so it's an extraordinary story, but unfortunately there's not enough of those extraordinary stories. Presumably, right through history, women have just not been able to overcome the obstacles.
All these brilliant minds wasted. You know, it's a tragedy.
Because they just didn't have the opportunity to have a scientific education.
Yeah, right. In my own family, I mean, my mum had to leave school at 14 to work in the family business, while her brothers, who were not at all as bright as she is, got to go to university. That's my point of view.
No, I agree. And she's never stopped regretting that.
Yeah, I mean, she's you know, went back to college and you know, she really has realised herself. But at the same time, she didn't have that opportunity. And our own daughter, Bo, who's now, of course, has the opportunity. She's studying maths.
But her professor, she's studying pure maths in the Sorbonne, and her professor has told us that there is less women. There's less girls now applying to go to study maths than there were 10 years ago. Absolutely,
and there are very few girls in her class. So I think it's a nice place to finish with Marie Curie, because she deserves the homage of this, dedicating this series to her. Tomorrow. This is the end of the series of conversations, but tomorrow will be available at the same time at the Clonmel Junction Festival to take some questions and have a chat if anybody's interested. So it would be really great to meet some of the people who've been listening in and hear what you have to say.
And thank you so much for listening. I'm looking forward to talking to you tomorrow if we can.
Goodbye. Thank you very much.